Hey everybody, welcome back to Bennett's Chemistry 12 tutorials. We're back at it. We're in the Redox section now. Last class we did an introduction to Redox, kind of what reduction was, what oxidation was, the fundamental principle of the whole thing. Also looked into oxidation numbers and how you can figure them out for every atom within a chemical species. Using our priority list and also how you can apply oxidation numbers to understand what's going on in a redox reaction. Which atom is undergoing reduction, which atom is undergoing oxidation. And then also the being able to label which of the two reactants would be considered the oxidizing agent and which of the reactants would have been the reducing agent. So we did all that last class. So, as promised, today is going to be a balancing redox reaction class, and there's actually going to be two classes in a row. So this one is going to be balancing a redox reaction using a half-cell method. And then next class I'm going to show you how to do using the oxidation number method. Okay, so there's two different ways. Both of them have their pros and their cons. Okay, so let's start with the half-cell method, which is going to be today. So the good thing about using a half-cell method, at least from my perspective, is number one, if you learn how to balance using the half-cell method, if anybody ever asks you what reaction would be considered the reduction half cell. So if you're asked for half of the overall redox reaction, if you've been practicing balancing equations, well, you've been practicing how to balance the reduction and balancing the oxidation, and then learning how to put them together to give you the overall. So if you're ever asked a half cell reaction, you've been practiced at it once you know the half cell method. The other thing that I like about the half cell method is it really gives you a really good understanding of the concept of a reduction and oxidation must happen, and the electrons that get transferred from the atom that's doing all the oxidizing and losing its electrons, the total number of electrons lost by that chemical species has to equal the number of electrons gained by the atom whatever's doing the reducing. Okay, and when you do this method, part of the process is you make the electrons balance between the two half-cell reactions. And by doing that, you kind of get that sense, okay, so this is the total number of electrons that get lost from this thing and gained by this thing over here. And you really understand that, okay? The other thing is it's a very, very clinical step-by-step process. And so if you know your steps and you get practiced at it and quite good at it, you tend to not make very many mistakes when you're balancing these equations. Now, you might say, what are the cons? It sounds like it's pretty good. Well, number one, it takes a little longer because you write down more, and it's a little bit more arduous to get through it. Okay, the oxidation number method is faster. So once you kind of get the concept of balancing an equation, and you can really see that there's two half cells and the total number of electrons are balanced, the oxidation number method is actually faster. You'll be able to go faster. However, it's a little bit harder in learning how to balance a half cell reaction. It takes a little bit more doing to figure that one out. So each one has its pros and its cons. Now, whichever method you decide you're going to end up using, maybe you'll use both depending on what the situation calls for. But you might say to yourself, well, I learned how to balance equations like in grade 9 and then grade 10, and I got pretty good at it at grade 11. Like, what's the big deal here? The numbers that we're going to be talking about, the equations are the chemical equations are much more complex. Okay, there's usually more things involved. As you can see, the one that I'm about to do on the board that's over here over my shoulder here, we're talking about polyatomic ions. It doesn't seem quite as simple. You're talking about like non-neutral things, not really obvious things. The numbers are a little bit crazy. And sometimes you end up with coefficients that are like wacky, like you end up with a coefficient of 32 instead of your typical, what you had maybe, a really complicated one in Science 10 might have had a coefficient of 6 or maybe even like 10. Wow. But these can have really crazy coefficients. And so doing, trying to balance redox reactions by trial and error, which is essentially what you did in grade 9, 10, and 11, with some kind of hints to make the trial and error a little bit easier. Trial and error with some of these ones, it would take you, a week of trial and erroring to find out what's going on with these things. Okay, so what I'm going to do is I'm going to show you the half cell technique today. I'm just going to show you that by going through one problem. That's it, just one. And then once you kind of see one, you kind of do your own practice and you kind of get in the hang of it. And once you kind of do a few, you'll be able to even show other people how it gets done. So what I've done over here on the board is, I told you, the half cell method is a very analytical thing. It's very step by step. Do this, then this, then this, then this. And so I've pre-written down the steps that you are going to do in order to do the half cell balancing method. Okay, so we're going to do a couple things. Number one, we're going to balance in what's known as acidic solution. Oh, that reminds me, I completely forgot about this. So the half cell method, although it can be done in non-solutions, like for a homogeneous gaseous reaction, the concept of this is you're going to be using water molecules and H pluses or OH minuses to balance the equation. And so if it didn't happen in solution, that may not make sense to you. Whereas if you had a homogeneous gaseous reaction going on, the oxidation number method doesn't necessarily require the addition of waters or H pluses, as you're going to see. Okay, so it might be a little bit more, might fit what your mind is thinking if everything was a gas. Okay, but we'll see. So there are a series of steps. Okay, and so I've written them all down here on the board. Take a snapshot of that. Write them down. Your teacher probably has given you a list. Whoever's teaching you how to do this, they'll come up with a series of steps, because it is a very step-by-step process. Do this, then this, then this, then this. Bang, there's your answer, type of thing. Okay? So what I'm going to do is I'm going to go through each one of these steps, and as I go through each step, I'll give a little bit of an explanation as to why you're doing it, what you're doing, what you're looking for, and things like that. Okay? So I've got this one up here on the board. Okay? And so the question would be, balance the following redox reaction. Okay, or maybe it's in a lab and you're doing this redox reaction like in a beaker, or you're doing a titration maybe where you're adding two reactants and they happen to do a redox reaction. And the very first thing you've got to do, if you're going to do stoichiometry, obviously, you have to have a balanced chemical equation, right? So you got to have this thing balanced. The concept of this is that the number of electrons transferred have to be equal. And so that's kind of the fundamental principle of this entire thing. And you'll see kind of when that happens along the way. So I've got this thing here. These two reactants, they are reacting to form Cl- and NO2. Now, step number one over here says, separate into two half cells. Now, what that means is each one of the reactants over here, okay, so each one of these two things over here, they have a partner over on the other side, and you can usually kind of follow specific atoms. Oftentimes, hydrogen and oxygen being really high on the priority list, they're oftentimes not part of the reaction. They're oftentimes kind of just along for the ride, forming bonds to form molecules. Because they have such high priority, it's unlikely they're changing. Okay? So unless you've got one in elemental form, chances are it's not changing. So what I'm looking for is I'm looking for partnerships of atoms, and you can, in a redox reaction, you can usually kind of see them. So in this one, you can see that there's a nitrogen on each side of the reaction. They're probably partners. And there's a chlorine on each side of the reaction, and they're probably partners. So probably this chemical and that chemical are partnered in one of the two half reactions. Whether it's the reduction or the oxidation, I mean, to be honest with you, I'm balancing this reaction. I don't care if I'm just coming up with a balanced overall reaction. If somebody said, give me the oxidation half cell, then I might look a little bit closer to see, using my oxidation numbers, which of the reactants actually oxidized, okay? But in this case, I'm doing the overall balanced chemical equation. So those two are going to be a partner. So when the first step says separate into two half cells, well, the first half cell will be N2H3 plus 1 turning into NO2. So that is the first half cell, whatever the N2H3 thing turns into the NO2. That is half of the reaction. The other half of the reaction is ClO4 -1 turning into Cl minus, and don't make the mistake that that's an iodine. Okay, if it was iodine, it would be having the little hat and the feet down at the bottom of the line. Okay, so got ClO4 minus turning into Cl minus. So these are the two half reactions. Okay, I separated them. So there are your partnerships. Okay, and so you'll have to first spot those partnerships, and it's usually, you can tell by the atoms. It's usually pretty obvious. Okay. Then what I do is I do the next 5 steps, so 2 through 5, to each one of them. And I just go through each of the two half reactions one at a time. I go through step 2 to 5 for the first one, and then I go back and I do step 2 to 5 for the second one. And then I carry on with 6 and 7 up there, okay? So I'm going to focus on the N2H3 plus 1 turning into NO2. And I'll go through each of the steps. So first step, balance non-oxygen, non-hydrogens. So I think that's self-explanatory. If you're not hydrogen, you're not oxygen. You try to make sure that the number of atoms on either side are equal to each other. So over here, on the top one, I've got 2 nitrogens. And over here, I've got 1 nitrogen. Okay, so I'm going to go fairly quickly through this because, like, you know how to balance an equation. So that part, I'm not going to spend a lot of time on. Okay, so I'm going to use some different colors here. So first thing I'm going to do is I'm going to put a 2 in front of that to make sure that I've got 2 nitrogens. Okay, so the nitrogens are balanced. Next step, so step number 3, balance oxygens by adding water. Now you might go, water? Where's water from? Like, what are you talking about? Water. I don't say water up there. Where's water from? Okay, so now, this is a couple of things. Number 1, this reaction involves ions up here. Well, ions don't just generally float around in space, right? They tend to move around in solution. So usually you're going to have ions when you've got a solution of them and they get to bump into each other. Well, I guess by definition, if you've got them in solution, there's going to be water molecules around. So typically what happens is this. The question will say, balance the following redox reaction. Okay, so the top one here. So balance that redox reaction in acidic solution. Or it will say in basic solution. It'll actually say it. Or it will just kind of over on the side, it'll do like something like this. Acid. Or if it's a lab situation, maybe you added sulfuric acid into the reaction. Or maybe ClO4 minus actually came in the form of HClO4, perchloric acid. So you have to recognize that this reaction is happening in solution, and more often than not, it needs to be an acidic or basic solution for this reaction to even happen. And you'll kind of see why here in just a little bit. Okay, so you'll see that. Now, when that is over there, when it says in acidic solution, or it says acid, or it gives you an actual acid as one of the reactants, what it is telling you is you have the ability to use, if you need to, water molecules, because they're present, they're floating around in there, and H+. Okay, so I guess technically we're talking about hydronium, but to make the balancing a little bit easier, we're going to use H+. Okay, you can always in your own mind be thinking of them as hydronium later on. But we're going to balance using H+. Okay, so that acidic is telling you you have those things available to you. Okay, so knowing that's kind of in our back pocket, maybe we'll need those things. So here we go. So balance the non-oxygen, non-hydrogen, we did that. Balance the oxygens by adding water molecules, okay, so H2Os. So you look at your half reaction, you find out where the oxygens are, if you have oxygens. Maybe you don't even have any oxygens. If you don't have oxygens, you're not adding water. But if you have oxygens, then you say to yourself, how many oxygens do I have on each side, right? So maybe the left-hand side has 10 and the right-hand side has 12. Well, the difference, but they're not balanced. So the difference between those two, between 10 and 12, is 2 oxygens are missing. Well, over here on the left-hand side, that would mean you should add 2 water molecules, because each water molecule has 1. And so that would bring the total oxygens up to being balanced. They're both at 12 now. Okay, so you're going to put water molecules into the half reaction to make sure the oxygens balance. Okay, so how does that look? So water molecules. So I have no oxygens over here on the left-hand side. Okay, I've got 4 oxygens over here because I've got 2 times 2, so I've got 4. That means I add 4 water molecules to that side. Okay, so the nitrogens are balanced, 2 and 2. The oxygens are balanced, 4 and 4. Okay, good. Next step. Balance the hydrogens by adding H+. Okay, so again, this said acidic, so this is where the H+ are going to come in. So this is, it means we have them, so I can put them wherever I need to put them. So balance the hydrogens using H+. Okay, well, where am I putting the H+? How many do I have? Over here, I've got, okay, let's add them up. 4 times 2, I've got 8 hydrogens from there, plus the 3 hydrogens from there. So I've got 11 on this side. I have 0 over here, which means I need 11 hydrogens. So I'm going to put 11 H+ over there. Okay, so far I have 2 nitrogens, 2 nitrogens. I've got 4 oxygens, 4 oxygens. I have 11 hydrogens, 11 hydrogens. So all my atoms now are balanced. Okay, so like the nitrogens, the oxygens, the hydrogens, they're all balanced. They're all present. However, one thing we didn't really get into a ton, and maybe your teacher emphasized it, and maybe not so much, is that, remember those whole conservation rules with chemical reactions? One of the conservation rules is that not only does mass and atoms and all that kind of stuff have to balance during a chemical reaction, charge must also be conserved. So that means that the total charge on the left-hand side of a reaction has to equal the total charge on the right-hand side. What it really means is all the protons and electrons are accounted for. All the things with charge are accounted for. So let's see just for a sec, and you'll see that it's not, if charge is balanced. So let's do the math. Water molecules are neutral, so 4 times 0 is 0. I've got one of these things, and that chemical is +1. So over here on this side, and I'm just going to draw it just temporarily. Over on this side, it's +1. Okay, so +1 on that side, total charge. Over here on the other side, well, the NO2 is neutral. 2 times neutral, or 2 times 0 is 0. 11 times +1. So over here on this side, it is +11. So we're talking about the entire side. And so you might have multiple things. You might have coefficients in front of things. It might be +3, and you've got 12 of them. Well, that would be +36, right? So you have to do the total math, and you're comparing the entire left side to the entire right side, which means charge has not been conserved in this half reaction. +1 here, it's +11 there. Okay, so I'm going to just think for a second here. Let's go to the next step. Balance charge, so we're at this stage now, balance charge by adding E- electrons. Each electron is worth -1. And so you're going to add enough negative charges to one of the two sides to bring the charges down to being equal. So you always add electrons to the side that is higher in charge than the other side. Okay, so this side over here is +1, this side over here is +11. Where would I add negative charges to bring those to the same charge? Well, I would add negatives over here to bring it down to +1. So then you say, well, how many negatives do I add? Well, hopefully you can do the math pretty quickly in your head. I need to add 10 -1 charges to this side to make this overall charge +1, which would then equal the charge over here. Okay, so that's what I'm doing. So this side, let me erase this so it doesn't get too busy over here. Okay, so I'm adding not 11, I didn't say 11, I said 10, +10 electrons. Okay? So +10 electrons. Now, that top one, we just finished step number 5. So I am done the top one. Okay, so I'm about to move to the second one here, the ClO4 minus going to Cl minus. But I just want to stop just for a little second here because I want you to think and see what you've got here. You have this half reaction up here where all the atoms are balanced, right? They're conserved. All the nitrogens, the oxygens, the hydrogens, they're the same on both sides. You've got the charge being conserved. The left-hand side and the right-hand side, they equal each other. You have a balanced half reaction because all the components of conservation are balanced. So you have a balanced half reaction. Which one is it? The oxidation or the reduction? It's one of the two. So it is, because the electrons are being produced, meaning lost from, this must be the oxidation. Okay, so the oxidation half cell is this one right here. And so if you were asked for this overall reaction, write the balanced oxidation half reaction in acidic solution, that's your answer. Half reactions always have electrons in them because they're only half of the overall redox reaction. So you would expect electrons to be kind of roaming around loose. The other half hasn't happened yet. So this is the balanced half one. It will not be, you won't see electrons in the overall because guess what? They're going to get used up in the next one. Okay, so that's what you've got. You've got your balanced oxidation, so this one better be a reduction, otherwise we messed up somewhere along the way. So let's go back to step number 2 and let's go through the whole thing again. Do it a little bit quicker this time. Okay, so once you get good at this, it goes pretty quickly. So balance the non-oxygen, non-hydrogen, 1 chlorine, done. Step 2 is done. Balance oxygens by adding water molecules. I've got 4 oxygens over here, I've got 0 over here. That means 4 water molecules over there. Balance hydrogens by adding H+. I've got 8, 4 times 2, I've got 8 hydrogens over there, I've got none over here. So plus 8 H pluses over here. Balance charge by adding electrons. And they're -1. So you're going to add them to the side that has the higher charge to bring it down to the other side. So don't just always bring it down to 0, bring it down to the other side. So over here we added so it came down to +1. Here, what have we got? We've got 8 times +1, so that's +8, -1, so +7. This side is +7. The other side, -1, neutral. This side is -1. So then you say to yourself, okay, I'm going to add negative charges to which side? To the side that's higher to bring it down to the other one. So I'm going to add plus 8 electrons over there. If you take +7 minus 8, you get -1. And that's what you're thinking about there. Once you've written in the electrons, you have balanced half reactions. So here is your balanced oxidation half reaction. Here is your balanced reduction half reaction. Okay? But we haven't balanced the overall reaction because I want you to think. A redox reaction is the reduction and the oxidation put together, right? So the oxidation, think of it this way, the oxidation is producing 10 electrons. The reduction is only taking up 8 of those 10 electrons. That means there's like 2 left over. Wait, that doesn't work. Okay, so now you have to start thinking. They don't necessarily just one of those and one of those. We have to make it so that the electrons produced by the oxidation equal the electrons gained by the reduction. That is the fundamental concept of balancing using the half-cell method. So I need to make this number of electrons there equal to that number of electrons there. Then we look at step number 6. So you're going to multiply each of the half reactions so that the electrons are the lowest common multiple. Okay, so you got to go back to your elementary school mathematics and try and figure out what's the lowest common multiple. What's the lowest common multiple between 8 and 10? Now, some of you will just go, well, why don't you just multiply this one by 8 and multiply that one by 10? Well, that's fine, except you're going to have to reduce at the end. So you're going to end up dividing by 2, because 80 is not the lowest common multiple. 40 is the lowest common multiple, which means I'm going to take this guy, take the entire thing, okay, so that entire reaction, I'm going to multiply the entire thing times 4. So every coefficient I'm going to multiply by 4. I'm going to take the bottom guy, that's not what I wanted to do. Oh yeah, that's what I wanted to do. Sorry. I'll go with blue. So I need to make that 40. So what am I multiplying by? Not by 4. I'm multiplying it by 5. Okay, so now think of it this way. The oxidation happens, there's your balanced oxidation, but it happens 4 times for every time the reduction happens 5 times. So 4 to 5 times. Well, the total number of electrons produced by this guy are going to be 4 times 10, 40 electrons in total produced. 5 times 8, 40. So this guy's going to produce 40 electrons when it happens 4 times. This guy's going to use 40 electrons when it happens 5 times. So they don't have to happen the same number of times. You just have to have the same number of electrons being produced and used. Okay? So now, what I have to do is I have to multiply each of those things. So I've written it as brackets, but what I'm going to do is if you're scribbling this on a piece of paper, like doing pen and paper stuff, you'll probably just cross out a coefficient and write a number up above, or like it gets a little bit messy. I happen to have a whiteboard. I can erase and I can put these things in. So here we go. I'm going to write it in blue. So I'm multiplying the top guy by 4. Okay, so this guy is 4 times 4, 16. 4 times 1 is 4. Oops. Wrote those a little bit close to each other. 4 times 2 is 8. 4 times 11 is 44. And 4 times 10 is 40. So I've gone through and I've taken every coefficient, multiplied it by 4. Okay? So then I go through the bottom one and I multiply by 5. So same deal. So 5 times 8 is 40. 5 times 8 is 40. This guy is 5 times 1. It's just going to be 5. 5 times 1 is 5. 5 times 4 is 20. Okay, so I've just done step number 6. Okay. Now what do I do? Okay, so now I have these two half reactions, and kind of the critical point, you can't do the final step until you see that your electrons are the same value, like same magnitude, 40 in this case, but on opposite sides. Which means that if you are going to, like, you're thinking of the two half cell reactions as being the two steps of a mechanism, it's not really two steps of a mechanism, they're all kind of happening at the same time. But if you think of it that way, that this 40 electrons produced up there cancel those 40 electrons used down there. That means that there will be no electrons in the overall reaction. And that's how you know you've got a balanced chemical equation. That's number one thing, is make sure the electrons have canceled. Okay, so that's a critical point. Now what I do is I cancel other things. Now typically what's going to cancel here will be the H pluses and the H2Os. The other things probably aren't, because they're part of the overall, they're part of the original reaction up here, so they're probably not going to cancel. Don't quote me on that, because that's not going to be 100% of the time. Sometimes some of them will. But you're looking really at the H pluses and the H2Os. So let's look at the H2Os first of all. I've got 16 of them there, and I've got 20 of them there. So think that 16 are being used up here, but 20 are being produced. What's the net? Well, the net would be, okay, and I think I need to go like this, a little bit of room over here. So I start by drawing the arrow. Now I know kind of what the answer to this one is, so I drew the arrow not exactly below, because I know I need a little bit more space over here. So the net is those 16 cancel entirely, and it leaves you with 4 of those water molecules. So there's a net production of 4 water molecules. Okay, and so, okay, I'm done water. Now on to the H pluses. I've got 40 H pluses right here, and I've got 44 H pluses over there. Again, 40 here, cancel those and leave behind 4 of those guys. Well, I've got 4 H pluses over here. So once you've canceled the electrons, because they're always going to perfectly cancel, that's why you're doing this, is to make them equal so that they disappear. Then you cancel the waters, you add them up, put them on the right side. Cancel the H pluses, add them up, put them on the right side. Then sometimes, like, they're not always going to be this way. Sometimes they're on opposite sides. Sometimes the water's on this side, the H plus is over here, and sometimes they're reversed. Sometimes they're both on the same side. So it's entirely dependent upon the actual reaction that you're doing. So don't think there's a standard side and place where the H pluses and the H2Os are going to be. Okay? Now I can actually look at the reactants and the products of this chemical reaction. So over here on the left-hand side, I've got 4 and 2 H3s and 5 ClO4s. Okay, so they're here and here, and they just come down here because they're not canceling with anything. And then over here, I'm left with the NO2s, 8 NO2s plus 5 Cl minuses. So there's your balanced overall reaction. Now look up up above here, there were two things that weren't in that original equation that ended up being in the overall reaction down here. The water and the H pluses were part of this overall reaction. So actually, they kind of did participate in what's going on here, okay? So having said that, is this actually balanced? Like, did we do this right? And how do you check? So you come back and certain things have to be conserved. So atoms have to be conserved and charge needs to be conserved. So I personally always check charge first because charge is kind of a tricky one that if you didn't do this right, charge never adds up properly. Okay, so I'm like 90% certain if the charge is balanced on either side, I probably did it right. So I'm going to do charge first. So on this side, I've got 4 times plus 1, that's plus 4. 5 times negative 1, so that's negative 5. Negative 5 plus 4, that's negative 1. So the left-hand side is negative 1. Over on this side, neutral. 4 times plus 1, that's plus 4. Neutral. 5 times minus 1, that's negative 5. Well, that side's also negative 1. So charge is balanced. Negative 1, negative 1. Okay, that's a good sign. That means it's probably balanced because charge is balanced. So what I do is you just should be able to go through fairly quickly and balance your atoms. So I'm going to just quickly go through all of them. Okay, so because you should be able to do this fairly quickly. 4 times 2, that's 8 nitrogens. 8 times 1, 8 nitrogens. Nitrogens, tick. Hydrogens. 4 times 3 is 12. None there. 4 times 2 is 8, plus those 4, that's 12. Hydrogens, tick. 5 times chlorine. 5 times 1, chlorine. 5 chlorines. 5 chlorines, tick. Oxygen, last one. 5 times 4 is 20. 4 times 1 is 4. 8 times 2 is 16. 16 plus 4 is 20. Tick. Oxygens are balanced. That is a balanced redox reaction in an acidic solution. Okay? Partway through, we also had a balanced oxidation half cell and a balanced reduction half cell if I was asked in some situation, which you're going to be later on. That's kind of why I do half cell in my own classes. You're going to be asked to do that. But there's your balanced overall reaction. Now, there's 2 more things that I wanted to show you. 1, what happens if it's in a basic solution? And then 2, net ionic versus formula equation. Okay, because what you've actually written up here is a net ionic equation. Okay, it's not a formula equation. So I want to just show you that one. Okay, so the basic solution one. Okay, to answer the question that if this said balance this reaction in a basic solution. Okay, so instead of saying acid, it says basic. The idea being that instead of having H pluses, you have OH minuses available to you. Now the process, like the steps would be ever so slightly different because you can't balance hydrogens using H plus when you've got OH minus, right? Like it doesn't work that way. So you can't really follow the same steps if it's a basic solution unless you balance it in acidic and then know how to convert it. Okay, so my rule of thumb, the technique that you use, your strategy for balancing in a basic solution will be to, 1, balance it in acidic, which is, that's balanced in acidic. So this is my answer in acidic. Okay, good. 2, convert it to hydroxide. Now, how do you convert to hydroxide? Here's what you do. You look at your equation and you focus in on the H pluses. Where's the H plus term? If there aren't any H pluses, then it doesn't matter if it's acidic or basic, right? It's the same thing in acidic or basic. You don't even need H pluses. However, this one does have H pluses. They're right here. Okay, so the 4 H pluses. Let's focus in on the 4 H pluses. So if I'm converting to a hydroxide, what I'm going to do is I'm going to add a certain number of hydroxides that will neutralize or balance the H pluses. So there are 4 H pluses. What I'm going to do is I'm going to add 4 hydroxides to this side. And when you add hydroxides and hydrogens together, what do they make? They make a water molecule. Okay, so if I have 4 H pluses and I add 4 hydroxides, they will make 4 waters. So I'm going to go plus 4 hydroxides, and they will make 4 waters. And just hold that thought just for a little second. But this is kind of like math class. You can't just add things to one side and not the other. You can do whatever you want. You can add whatever you want as long as you do it to both sides. So if I add 4 hydroxides over here, because there were 4 H pluses, if that number was 112, I would have added 112 hydroxides. Okay, that's the idea. So I add 4 hydroxides there. I'm going to add 4 hydroxides over there. So I add them to both sides. Now, when I add 4 hydroxides over here, that makes 4 H2Os. Right? So those two things kind of cancel each other out. 4 H pluses and 4 hydroxides make 4 waters. That's why I'm adding the exact same number of hydroxides. So now what I do is I re-add. I just add everything up now. Okay? So here's what I've got. I've got 4 N2H3 plus 1 plus 5 ClO4 minus 1 plus, now I've got 4 hydroxides over here. So the reactant side of my equation now has an extra little reactant over there. It's got the hydroxide over there. Now over on this side, well, I already had 4 water molecules and I'm adding 4 more, so now I've got 8. Sometimes when you convert to a basic solution, you add hydroxide. Sometimes the waters end up being on opposite sides and you cancel before you combine them. These happen to be on the same side, so I combine them into 8. The H pluses are now gone, right? Like these things disappeared to make the 4 new water molecules. So now they're gone. So now I just move on to plus 8 NO2s plus 5 Cl minuses. Okay? Now, that would be your balanced redox reaction in a basic solution. Here it is in an acidic solution, that original one that I did. And so if someone asks you, balance in a basic solution, my suggestion, what I teach in class, is I balance it in an acidic solution and then I convert it to a basic so that you have to remember one rule of thumb. Some of you are going to say, well, I'll just wait for the oxidation number technique tomorrow and then it'll be much easier. Okay, now the very last thing is the net ionic versus the formula equation. So I want to go back and I want to look back at this guy. I'm going to rewrite that. I'm going to rewrite that. 4 waters and 4 H pluses. Okay, now, how do I know this is a net ionic equation? Because it's giving me everything in ions. And really, if you had a solution of stuff, like I can't go get a bottle of Cl minus. It has to come along with a cation. Now, the reason why the cations aren't in there is because they're spectators, right? We make a solution where the ions we don't want to participate, we make them so that they're spectators. They're there, they float around, they provide charge to neutral this to make the overall solution a neutral charge. But they don't do anything. Okay, so for example, the ClO4 minus right there, maybe it actually was KClO4. So the potassium ion was part of this compound, this solution. So actually, maybe this was KClO4. And you may have even been given that in the actual equation. You have to recognize that the K is a spectator ion. This NH3, well, that's a polyatomic cation. So maybe it was attached to N2H3. Maybe it was attached to nitrate ions. And so, well, that's a crazy looking deal. So maybe the NO3 did nothing. And so it didn't react. It's a spectator. It just came along for the ride. Which means that over here on the product side, you would have had to have had those ions show up over here on the other side somewhere. Okay? So the reaction that you're going to produce here at the end, all the cations would have been attached to a spectator anion. All of the anions would have been attached to a spectator cation. So chances are that here at the very end, right? So these guys would have been attached to a nitrate, an NO3 negative 1. So you would have had 4 N2H3 NO3s, which means 4 nitrate ions were also present. They were floating around. They didn't do anything. They were spectators, and that's why we took a solution of that guy. And 5 KClO4s. Again, the potassium was a spectator, but it didn't do anything. But there it is in the formula equation of the salt that was dissolved in the water originally. 4 waters, well, it's not an ion, plus 4 H pluses. Well, the 4 H pluses, if you're going to put it as a formula equation, even if it's not like stuck together into a compound, it would have the anions. Well, guess what? 4 nitrates went through this process. They're probably stuck to that cation, in theory. So you would write 4 HNO3s plus 8 NO2s. So every single one of the ions so far has been neutralized. Not neutralized. Its charge is neutral by having the spectator ion attached to it. So the last one are the Cl minuses. Well, there were 5 potassiums along for the ride here. So guess what? They showed up over here. Now, oftentimes, certainly in Chem 12, oftentimes, you'll be given this and you'll be asked to give it in the net ionic form. Okay, so you'll be asked to give it in this form right here. In practicality, though, like in a practical lab situation, for example, you might go get those solutions, mix them together. They might produce those down there. Okay, and so you have to be aware of the reality of the chemistry versus the, okay, so net ionic is really just showing you what ions actually participate in what's going on here. Okay, so be aware of one or the other. Now that you've got a balanced equation, you can apply stoichiometry, right? So if you knew how many moles of this thing you reacted, you'd be able to tell how many moles of that thing, or how many moles of NO2 you'd be expecting, or if that was a gas and it was being produced at RTP, what volume of that gas might be produced, and all of those kind of fun things that go along for the ride, okay? So that's balancing your chemically redox equation using your half-cell method. There's a lot there, but if you take the steps and just kind of say in your mind, okay, do this, then this, then this, then this, then this, and you kind of get it into a bit of a flow and a system, you'll be able to balance these things no problem, even if they look really complicated and you've got these massive looking numbers. Okay, so now go do some practice that your teacher has assigned, or even go online, find some redox reactions to balance and give it a whirl. See how you do. Okay, we'll see you on the next video for balancing, also balancing, but using oxidation number method, which, like I said, has the pro of being maybe a little bit faster once you get good at it, but it has the con of you don't really see the two half reactions being separated from each other. Okay, so we'll see you then.